Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. This is Chemical Equilibrium Volume 4. That's right, we are picking up right where we left off with our discussion on chemical equilibrium. And you may be asking yourself, hey Ben, where can I find volumes 1 through 3? Good question. I will answer it for you now. There is a playlist called Chemical Equilibrium Live Streams. It'll be in the description of this video, and it's not too hard to find it on my YouTube channel page. So, all right. Just a couple of housekeeping things. I was watching a couple of my recent streams, and I think the audio had some problems. It was like an echo sort of sound. I believe that I fixed that, but anybody in the chat who would like to participate and let me know how the audio sounds, I would certainly appreciate it. And also feel free to participate in the chat and talk about whatever you want. If you want to contribute to the discussion, if you want to ask a question, if I go over something too fast, if I'm not making any sense, I would highly encourage your participation in the chat. And better yet, if you want, you could even call in to the show using Discord. There's a link right down there in the description. It'll connect you to the call-in room. So, all right. Without further ado, let's get right into Chemical Equilibrium Volume 4. So here it comes. All right, going to, there it is. Okay, already got a question in the chat. It says chemical equilibrium is the KEQ thing, right? Right you are, sir. You have come to the right place if that's what you're looking for. So I'm going to do the same thing that I always do, which is to review briefly. That's the goal, to review briefly the content that we went over from the previous stream. The previous stream was Volume 3. So last week was all about finding the concentrations of reactants and products at equilibrium. And we looked at two different scenarios on how to find equilibrium concentrations. One of those scenarios was this one right here, when you are given all but one of the equilibrium concentrations of all of the reactants and products, and that's pretty straightforward. You have one equation, you have one unknown, algebraically solve for your unknown, put all your values into the calculator, and that'll give you the answer. The second scenario in which you might be asked to find the concentrations of reactants and products at equilibrium is much, much more difficult. And that's when you only have the equilibrium constant and the initial concentrations of the reactants and products. And in some cases, as we saw a week ago, you might even need to use the quadratic formula in order to solve that kind of problem. So we went through a couple of examples last week, one in which the quadratic formula wasn't necessary, and then the latter example was one in which the quadratic formula was necessary. And as we saw, those problems are very, very long-winded, very, very tedious, and take a lot of time. So if you're taking a test, it would really chew up a lot of time and put you in danger of running out of time. So just to recap, I'm just going to do a brief walkthrough of the process by which you would find equilibrium concentrations of reactants and products when you're given the equilibrium constant and the initial concentrations of the reactants and products. So in this example, let's just say we have this reaction here where we have A reacting at equilibrium to form 2B, and let's say that the equilibrium constant with respect to concentration, which we call Kc, is equal to 10. And let's assume that we don't have any B in this mixture. Initially, we start out with just the reactant A in this mixture at a concentration of 1 molar. Okay, so we have this reaction equation right here. The equilibrium constant is 10, and the initial concentration of the reactant A is 1 molar, and we don't have any B. So then the question would become, well, what are the equilibrium concentrations of A and B? How would we go about solving this problem? And the answer is, well, there's a multi-step solution, but the first thing that you would do is you would construct an ICE table, and you would populate that table with the values that you know, and you would use the stoichiometry of the reaction to determine what the change must be, by what quantity the reactant concentration and product concentration must have changed. So for initial, that's pretty straightforward. Concentration of A in this case is 1 molar, concentration of B is 0. The change, well, we know that since we start out with nothing but a reactant, its concentration is going to decrease by some amount that we'll call X as it approaches equilibrium. If the reactant A is decreasing by 2X, and that means by X, excuse me, if the reactant A concentration is decreasing by X, then the product B must be increasing by 2X. So recall you want to put whatever number that is the coefficient in front of the chemical formula in that for that reactant or product. You want to put that in front of the change, in front of the x value. And then at equilibrium, it's just, in the case of reactant A, it's 1 minus x, 1 molar minus x. And for B, it's 0 plus 2x, or just simply 2x. So at this point, you have these expressions that you can plug in to the equilibrium constant expression, also known as the law of mass action. So Kc, the equilibrium concentration with respect to concentration, is equal to concentration of B squared over concentration of A. And again, this is just what we've learned from the very, very first lesson on chemical equilibrium. The equilibrium constant is the products raised to their coefficients divided by the reactants raised to the power of their coefficients. So if we take the 1 minus x and we substitute it for concentration of A, and we take the 2x and we substitute that for concentration of B, we end up with this expression here, in which we have 2x quantity squared divided by 1 minus x is equal to, in this case, 10, because recall 10 is just the given value of the equilibrium constant. So you have this equation here, and by rearranging this equation, you end up with this equation over here, which is 4x squared plus 10x minus 10 is equal to 0. This is what we call a quadratic equation. So for a quadratic equation, you would use the quadratic formula to solve for x. And so just to review that briefly, anytime you have an equation of the form ax squared plus bx plus c is equal to 0, then the value of x is going to be, there's two solutions. It's going to be negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's what we would, this is the method that we used a week ago using the quadratic formula to approach solving for the equilibrium concentrations of reactants and products. Now, I'm going to stop this right here. I mean, because the algebra is something that we are pretty much already familiar with. But that's just, again, the whole purpose is to review the process, right? You construct your ICE table. That gets you the expressions for equilibrium concentrations in terms of x. You take those x expressions and you substitute in them into the law of mass action, and then you simplify the equation down, write the equation in the form ax squared plus bx plus c equals 0, and then use the quadratic formula to solve. So that's what we did last week, and that's a very, very long, very tedious process. It requires a bunch of algebraic steps, and anytime you have more algebraic steps, there's always the likelihood that you'll mess up on something and completely throw your answer off. So wouldn't it be nice if there was a way to solve these problems without using such a long, complicated, convoluted procedure? That would be pretty awesome, wouldn't it? I think it would. Well, lucky for us, there is a way by which these problems can be performed that is much, much easier with much, much fewer steps. So that's what we're going to talk about today. We're going to talk about using approximations in equilibrium problems. So we're going to talk about how to use an approximation for x, right? And then we're also going to learn how to check the validity of that approximation, right? Because you need to know whether an approximation is good or not good. So we're going to figure out how to check that. So let's go to a new problem. Let's say we have the same reaction, right? We have our reactant A reacting reversibly to form 2B. And now let's say that our equilibrium constant is 1.0 times 10 to the minus 5. That's a pretty small number, isn't it? It's like 0.00000, right? 1.0 times 10 to the minus 5. And let's say that initially we have the reactant A, we don't have any B, and the concentration of that reactant A is 1 molar. So if we think about this, we know that our equilibrium constant is very, very, very small. What does that mean? Equilibrium constant is very, very small. That means the ratio of the products raised to their coefficients divided by the reactants raised to their coefficients is very, very small, which means that the concentration of the reactants relative to the products is going to be very, very large. So we wouldn't expect this reaction to change very much. We wouldn't expect the concentration of A to decrease by very much until it reaches equilibrium, because that equilibrium constant is so small. It is a reactant favored equilibrium, right? So if the equilibrium constant is small and the initial concentration of your reactant is large, then there may be an approximation that we could use. So let's talk about how to do that. So just like before, we would construct an ice table, right? So initially we have one molar of A, we have 0 B, the change minus X in the case of our reactant A, plus 2X in the case of our reactant B. And at equilibrium, that's 1 minus X for A, and B is 2X, right? And so at this point, just like we saw before, we take these 1 minus X and 2X and plug them into the equilibrium concentration expression, and we end up getting something like this, where we have 2X quantity squared over 1 minus X is equal to 1.0 times 10 to the minus 5. So at this point, what I'd like to do is I'd like to grab the information that we have here. I missed it. Let's see. I'm going to grab this information and I'm going to bring it to the whiteboard, because that is how we're going to show how these approximations work. So here we go. All right, so can everybody see that okay? Hope I haven't made it too big. I want to make sure I have plenty of space to work with here. Okay, so again, so far, this problem hasn't differed at all from the way in which we've solved equilibrium problems in the past, right? You set up an ice table, plug in your initial values, use the stoichiometry of the reaction to figure out whether it's X, 2X, minus, plus, etc. You arrive at your equilibrium expressions, and then you plug those into your expression for equilibrium constant, right? And that leads us to this equation that we have right here, right? So at this point, this is where the approximation comes in. So I'm going to say that I think that X, right, is very, very small compared to the number 1 for reasons that I discussed earlier, right? We have a fairly large concentration of our reactant, and we have a very, very low equilibrium constant, which means the reactant concentration isn't going to decrease by very much to reach equilibrium, right? That's what a low equilibrium constant means. It's reactant favored. Concentration of reactants relative to products is high when your equilibrium constant is very, very low, right? So what I'm going to do is I'm just going to cross out that X and just kind of pretend it's not there. And I know that sounds kind of silly, right? It seems kind of silly. Like you can't just remove what you don't like from a chemical equation. Like that's not how mathematics works. And that was kind of my reaction when I first started looking at these approximation problems too. But we will explain why in just a moment. So what I'm going to do is I'm going to remove the X. So now what I have is something that's greatly simplified, something that I don't have to use the quadratic formula to solve, and make solving the problem a lot easier. So what I have is 4x squared, right? Because if I take this 2x and square that 2x, it ends up being 4x squared, excuse me, over 1, which, okay, anything over 1 is just itself, right? 4x squared is equal to 1.0 times 10 to the minus 5, right? And so if I rearrange this, if I just divide both sides by 4, I get that x squared is equal to 1.0 times 10 to the minus 5 divided by 4. And then finally, if I take the square root of both sides, then I get x is equal to the square root of 1.0 times 10 to the minus 5 divided by 4. So if anybody would like to throw this into their calculator and solve for it, I would appreciate it, because then I'd be able to compare the number that I got to the number that you got and make sure we're right. While I'm waiting on anybody who wants to calculate this, just want to say, if you find value in this stream, I would certainly appreciate you slapping a thumbs up on it. And if you're feeling really generous, you can consider sending a super chat. Hopefully I don't have to wait as long this stream for chat messages after I ask a question because I actually changed the latency settings. I switched from normal latency to low latency, which might have a negative effect on the video playback. It might make things look not so good. This is when I rely on your feedback to tell me how the video looks, how the audio sounds, if the content is helpful, if it's not helpful, everything. I rely on your feedback. It's very, very, very important. Okay, so it doesn't look like anybody is volunteering to submit their answer to this problem here, so I will just go ahead and write out what I have. So what I got when I computed this is that x is 0.00158. So this is the value of x that I got. So again, what have I done here? I've done essentially the same thing as before, only I narrowly avoided using the quadratic formula by reasoning that the value of x is probably very, 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 very small compared to the value of 1, which is what I'm subtracting x from. Okay, so imagine that you step on a bathroom scale with a marble in your pocket, right? You step on the bathroom scale with a marble in your pocket and you record the reading, whatever weight it shows on the scale. Now imagine that you took the marble out of your pocket and then stepped back on the scale without the marble. Unless you have a freakishly sensitive bathroom scale, the reading is not going to change, right? That doesn't mean that the marble is weightless, but it does mean that the weight of the marble is negligible compared to the weight of your body. And that's what this approximation is all about. It's about understanding and reasoning that this is probably much, much, much smaller than the number that it's being subtracted from. And I say reasonably, probably, there's actually a way to check to see if the approximation is valid. And so at this point, let's see if I can, I think I'll go back to the PowerPoint. I think there's a PowerPoint slide about this. So this is what I got for x. Of course, if I believed that this approximation is valid and I wanted to compute the equilibrium concentrations of A and B, it's pretty straightforward. I would just refer back to the equilibrium row of my ICE table, and for A it would be 1 minus this value, and for B it would be 2 times this value. So I hope that's pretty straightforward. So that's how to solve an equilibrium problem using the, some people call it the x is small approximation. The x is small approximation. So I'm going to go back to the PowerPoint. Just bear with me. Okay, yeah, we have a slide for that. And okay, so we're back at the PowerPoint. Okay, so we use that method, that little trick, and that trick relies on the x is small approximation to be valid. And so there are a couple of ways by which we can check the validity of the x is small approximation. So the first thing that you would do is you would divide x by the number it was subtracted from. So in our case, just going briefly back to the whiteboard, the number that it was subtracted from was that number 1, right? 2x quantity squared over 1 minus x. So you would take that value and you would, the value of x, the 0.00158, and you would divide that by 1 and it would be 0.00158. So here I'll actually perform that calculation myself. So if I have 0.00158, right, and I divide that, I'll just do this in blue, and if I divide that by the number it was subtracted from, that's 1, then I'll end up with 0.00158. So in this case, it didn't really mean much that we divided by the number it was subtracted from, but that's how it was done. So going back to the PowerPoint real quick, so once you divide x by the number it was subtracted from, there's going to be one of two possibilities. Either x will be less than 5% of the number it was subtracted from, or x will be greater than or equal to 5% of the number it was subtracted from. Okay? If it's less than 5%, then we consider that a valid approximation. And if the value of x is more than 5% of the number it was subtracted from, that's considered an invalid approximation. So there's a little bit more work that needs to be done if you were in a situation where you determined that the approximation was not valid. So if we go back to our example on the whiteboard, so if we have 0.00158, right, and if we multiplied that by, we'll do it in green, if we multiply that by 100%, well, this ends up being 0.158%, which is much, much less than 5%. So in this case, the x is small approximation is valid, but it won't always be. So never just assume that it's going to be valid every time you do it. You have to check to make sure it's valid, and if not, there's something else that you have to do a little bit more work, unfortunately. So going back to the PowerPoint here, so let's suppose you do one of these equilibrium problems and you apply the x is small approximation. You divide x, the calculated value of x that you got, by the number it was subtracted from, and you get a value of 5% or greater. That means your approximation is invalid. Okay, so what do you do at that point? Well, you have two options. You can either start the problem all over again using the quadratic formula to solve for x, which is, again, what we did a week ago and is very, very tedious and requires a lot of work. Or you can use something called the method of successive approximations. So the method of successive approximations involves just taking that x that you calculated, reinserting it into the equation to solve for x again. And this process, this reinserting of x into the equation and solving for it, can be repeated over and over and over again. And it'll be repeated over and over again until the volume or the value of that x stops changing from one iteration to the next. So one of the problems that we're going to do, I think, has an example of using the method of successive approximations, but it's not as easy as when you just have a valid approximation on the first attempt, but it is, in my opinion, still much easier than using the quadratic formula. But of course, you are welcome to be the judge of that. By the way, if anybody has any questions, comments, concerns, or other feedback, please feel free to drop it in the chat. I would love to hear what you guys are thinking. And yeah, so let me know. All right, so I think we are at the point where we can do a couple of practice problems. Okay, so we're going to do some practice problems by using approximations in equilibrium problems, so we don't have to use that stinking quadratic formula. So this problem says to consider the following reaction where we have SO2Cl2 reacting to form SO2 and Cl2. And according to this problem, we have a equilibrium constant with respect to concentration of 2.99 times 10 to the minus 7, and that's at 227 degrees Celsius. And it says that initially the reaction mixture contains SO2Cl2 at a concentration of 0.175 molar, and it says what is the concentration of Cl2, one of the products, at equilibrium. Okay, so I'm going to go ahead and copy this problem down and take it to the whiteboard. Let's delete all of that. Okay. I'm just copying and pasting what I need into the whiteboard before I switch over to it. There's one more thing I need. There it is. Okay. Okay. All right, I think we're ready. So, and again, all I've done here is just copied and pasted the information from the PowerPoint slide onto the whiteboard so that I can freehand draw, write things down, stuff like that. Okay, so As you can see, I've also copied and pasted an ice table into this, a blank ice table, because we're going to need one, right? So that's kind of where we want to get started, right? So I'm going to start filling out my ice table. So I'm going to have 3 chemical species. I'm going to have the concentration of SO2Cl2. I'm going to have the concentration of SO2, and I'm going to have the concentration of Cl2, right? So initially, what are our reactant and product concentrations? Well, it says here that our initial SO2Cl2 concentration is 0.175 molar, so I'll go ahead and fill that out, 0.175. Doesn't say anything about having any SO2 or Cl2 initially, so those are both 0. This is the only thing we have in the reaction mixture initially. As far as the change goes, in this case, it's pretty straightforward because we have coefficients of 1 for every reactant and product in this equation. So for SO2Cl2, it's going to be minus X, and for SO2 and Cl2, it's going to be plus X. And so equilibrium, initial and change come together to make your equilibrium, right? So I have 0.175 minus X for my SO2Cl2. And for both SO2 and Cl2, it's simply just 0 plus X, which is just X for both of these things, right? So I hope everybody is still following. If you're not, I would hope that you would let me know, because these kind of things are important. I don't want to leave anybody in the dust. I think I'm working pretty slowly, though. I think I'm working at a pretty slow pace. And that's another thing. If you think I should go faster with these, let me know. You know, it's like, hey, stop beating around the bush and get to the point. You know, we can handle it. Let me know. Either way, whether I'm going too fast or I'm going too slow or it's just right, let me know. All right. So at this point, we have these equilibrium values in terms of X for all of our reactants and products, right? And so we know that Kc, I'll write this up here, is equal to the concentration of SO2 times the concentration of Cl2 divided by the concentration of SO2Cl2. And again, that's just the law of mass action, right? Products raised to their coefficients divided by reactants raised to their coefficients. So we know that value, this equation is correct. And so we also know that Kc is equal to 2.99 times 10 to the minus 7, which is equal to, if I just go ahead and take these equilibrium values for all the reactants and products and substitute them in up here, I've got, what do I got? So for SO2 and Cl2, I have X times X, and for, that's a really not so flat fraction bar. Let me try that again. And then for the denominator of this, it's going to be 0.175 minus X. Now, of course, X times X, that simplifies down to X squared. So I'll go ahead and make that a little bit cleaner there. And then at this point, we're going to try that approximation to see if it works, right? So I'm going to take this X here, and I'm going to assume, and again, all that I'm doing with this approximation is, sorry, I accidentally just clicked on something I didn't want to click on. Okay. All that we're doing with this approximation is we are approximating that the value of X is much, 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 much smaller than the number that we're subtracting X from. So we think that X is much, much, much smaller than 0.175. If it is, then the approximation is valid. If it's not, then it's invalid. So let's go ahead and calculate as if the approximation is valid. So I'm going to just strike out this X, right? And that simplifies the equation greatly. So we end up with 2.99 times 10 to the minus 7 is equal to X squared over 0.175, right? And so if I rearrange this equation, basically what I'm going to end up with is that X is equal to the square root of 2.99 times 10 to the minus 7 times 0.175. So all I've done is just kind of rearrange this equation to isolate x all by itself. And so that is how we are going to calculate it. If anybody is following along and would like to share with me what they got if they are performing this calculation, which I highly encourage, I'll wait just a second for you to do so. By the way, I haven't mentioned it yet. I'm like 30 minutes into the stream, but happy Mother's Day, everybody. I don't know if the people watching right now are in a culture or country where they celebrate Mother's Day, but here in the U.S. we celebrate Mother's Day just to kind of give props, give appreciation to all the great mothers out there. So that includes my mom, that includes my wife. We had some good times. I spent a lot of time with the girls myself so that I could give my wife the gift of free time, of alone time, doing things on her own terms. And it was good. I had a good time too. Good time with my daughters. All right, so it doesn't look like anybody is going to solve this, so I'll go ahead and do it. So the value that I got x is equal to where is it? I got 0. I'll just do it in no, I don't want to do it in scientific notation. It's going to be 0.000229. Very, very small number, right? 0.000229. So there's a good chance that this is a valid approximation because this x is very, very small compared to the 0.175, which is what we subtracted it from, right? So again, we're going to check to see if the approximation is valid by taking the ratio of x to the number it was subtracted from. And again, if it's less than 5%, yay, we're done. It's a valid approximation. If not, we either have to go all the way back and start with using the quadratic formula, or we can use the method of successive approximations. Throw x back into the equation, solve for it again, keep doing that until the value of x does not change with each iteration. All right, so let's test this approximation. So I'll go ahead and grab a blue pen and kind of work over here. So again, what we're going to do is we're going to take the value of x, 0.000229, and we're going to divide that by, again, I don't know why my fraction bars are all wavy like that. That's a little bit better. We're going to divide that by the number we subtracted it from, which is 0.175. And so what value do we end up getting here? Well, the value that I got was, let's say we just multiply this by 100% just to make sure it's expressed in terms of a percent. And what I got was 0.13%, which is much, much less than 5%, which means in this case, the approximation was valid. So it's always important to remember what the problem is actually asking you. The problem is asking us what is the concentration of Cl2 at equilibrium. So in order to solve that, we need to refer back to our ICE table. So Cl2 in that column at equilibrium in this row, it's just simply equal to x. And so in this case, the concentration of Cl2 is equal to 0.000229 molar. So that's how you solve an equilibrium problem, by using the x is small approximation and then testing the validity of that approximation. In this case, it turned out to be valid, but it won't be in every case. So I think we're going to do one more example in which the x is small approximation is not valid, and see if we can solve that. So I'm going to go ahead and delete all of that. So if you guys will bear with me for just a moment, I'm going to go back to the PowerPoint, and yeah, we have another problem here. Okay, so this will be the last problem that we solve before we're all wrapped up, and then I think this and then just one more volume next week is going to pretty much have chemical equilibrium wrapped up. So all right, so let's see. So this problem says to consider the following reaction, where we have 2H2S reacting to form 2H2 plus S2. And the equilibrium constant in this case is 1.67 times 10 to the minus 4 at 800 degrees Celsius. And the problem says that we have a 0.500 liter reaction vessel, initially containing 1.25 times 10 to the minus 4 moles of hydrogen sulfide, H2S. And we want the equilibrium concentrations of H2 and S2. So this is a pretty interesting problem. So I'll go ahead and just put all this stuff into the whiteboard. Let's see. So you're in there. And then I'm going to grab me an ice table because I know I'm going to need one. And put that in there. Okay, so I'll switch it back to the whiteboard. There we are. And there's the problem. I'm not sure if that's big enough for you to read. I know that I'm going to need a lot of space to do what I need to do. This is going to be a very long problem because I've solved it already. But yeah, I think that's enough. I think that's probably big enough for you guys to read pretty well, pretty decently. So, all right. So, again, we start with our ice table. So I'll go ahead and sort of populate the labels of the columns. Each reactant or product will get its own column. So we're going to have H2S, right? And we're also going to have H2. And finally, we'll have S2. So we want to know what the initial concentrations of everything are. Well, the only thing that it says we have is H2S. So that means that the concentration of H2 and concentration of S2 initially are both 0. But it doesn't actually flat out give us the concentration of H2S. It just tells us how big our reaction vessel is and how many moles of H2S we have. We actually have to do some work to calculate what the initial concentration of H2S is in this case. So in this case, the concentration of H2S is pretty straightforward. It's just going to be the amount of H2S in moles, which in this case is 1.25 times 10 to the minus 4 moles. 0.25 times 10 to the minus 4 moles. That's just given by the problem, divided by the volume of the reaction vessel, which is 0.500 liters. And so solve that, and you'll get the initial concentration of hydrogen sulfide in molar, which is the same thing as moles per liter, right? So I'm not sure if anybody's trying to calculate that, but lucky for me, I already have. It's kind of like the cooking shows where they already have like a turkey that's done that they pull out of the oven just so that they can save time showing you everything. So the concentration of H2S initially is, what is it? And feel free to check me. Feel free to check to make sure I'm doing this right. So what I got was 2.50 times 10 to the minus 4 molar. That is the initial concentration of hydrogen sulfide. And again, all we did was we just took the moles of it, divided by the volume, and presto. Initial concentration of H2S. Now, as far as the change goes, right, remember we have to take into account the stoichiometry of the reaction, right? So it's going to be minus something times x. In this case, that something is going to be 2x. The coefficient must always go in front of the change, the x value. So it's going to be minus 2x for H2S. For the hydrogen, the H2, it's going to be plus 2x. And then for the S2, it's going to be plus x, right? With an understood 1 in front of it, right? Because there's an understood 1 in front of the S2. And so at equilibrium, what are we going to have? We're going to have 2.50 times 10 to the minus 4 minus 2x. That's our H2S. And then for H2 and S2, it's simply going to be 2x and x. So those are all our equilibrium concentrations for the reactants and products expressed in terms of x, right? So I'm going to give myself a little bit of room. Whoops, that's not what I was trying to do. I'll just use the pen again. I'm trying to erase some stuff to give myself as much room as possible because this is going to be a very, very long problem. Also, I'm going to try to reduce the thickness of my pen, so hopefully I'll be able to, yeah, that looks good. Hopefully I'll be able to write a little bit more with a thinner ink on this pen. All right, so we know our equilibrium concentrations in terms of X, right? So we know that the K sub C is going to be the concentration of H2 squared times the concentration of S2 divided by concentration of H2S squared. And again, that's really the same thing we've been looking at all along, the law of mass action, products to their coefficients divided by reactants raised to their coefficients. And so if we take our concentrations in terms of X and we plug them into this, well, what is that going to look like? Well, the concentration of H2 is 2x, so that's going to mean that we will have, I'll just put the 2x right here. So 2x, that quantity squared. Concentration of S2, that's going to be x at equilibrium. So I'll just insert that x in there. And then for the concentration of for the denominator rather of this expression, it's going to be this whole thing squared. So let me erase this. And so we're going to have, what are we going to have? 2.50 times 10 to the minus 4 minus 2x, and that whole thing is going to be squared, right? And that's going to be equal to the equilibrium constant, which, as given by the problem, was 1.67 times 10 to the minus 4. Okay, so lots going on in this problem. So again, if anybody has any issues, if anything looks confusing, anything at all, just stop me at any time. I am happy to hear your feedback no matter what it is. All right, so at this point, again, what we're going to do is we're going to use the X's small approximation to dramatically simplify our math here. So this 2x squared times x, I'm going to go ahead and simplify that down. So 2 squared is 4, x squared is x squared, right? And you tack on another x, that makes it x cubed. That ends up being x cubed. So this whole thing ends up being 4x cubed, right? And so we think that x is small, so we're going to delete that from the expression, right? And so I didn't write that down very well. This looks kind of jumbled over here. I'm not sure if you can read that or not, so I'm just going to rewrite that whole thing. So that ends up being 2.50 times 10 to the minus 4. 2.50 times 10 to the minus 4, that squared. So this doesn't look super simple, but it is much, much easier than if we didn't trim off that 2x and apply the approximation to this. So that ends up being, so if you take 2.50 times 10 to the minus 4 and you square it, that value is going to end up being, what is that? That ends up being 6.25 times 10 to the minus 8. So all I did was just take that value and I squared it to get that, right? Got a message in the chat from a name that I would have a very difficult time trying to pronounce. I'll just call you Fan because that's like the last part of your name. It says, good explanation. Thanks, man. I appreciate it. And I would also appreciate if I was doing any bad explanations that you would let me know about that too. All right, so let's continue. So all we're doing is we're just kind of simplifying this equation on our way to solving for x. So at this point, we end up getting, what is it? We end up getting 4x cubed. I'll just write it in. 4x cubed is equal to 1.67 times 10 to the minus 4 times 6.25 times 10 to the minus 8. And again, all I did there was just multiply both sides of this equation over here by this denominator of this fraction over here, right? So that's how I got that. And so if I want to get rid of the 4 in front of the x cubed, I need to divide both sides by 4. So that's going to be x cubed is equal to this whole thing divided by 4. And then finally, if I want to get rid of that cubed right there, I need to take the cube root of this entire thing. So it's going to be the cubed root of this whole, wow, I'm going to try that again. I do not have a very steady hand. So we have the cube root of 1.67 times 10 to the minus 4 times 6.25 times 10 to the minus 8 divided by 4. If anybody wants to take a stab at solving this, and you can compare it to the value that I got, that would be greatly appreciated, because sometimes I'll just confess, I do not have a lot of time to prepare for these live streams. I spend a lot of time with my daughters every day, and I just try to squeeze in this whenever I can. But I'm just basically stalling while somebody hopefully can solve that for me. Cube root of 1.67 times 10 to the minus 4 times 6.25 times 10 to the minus 8 divided by 4. So, by the way, I've noticed a couple more people have hopped in the stream. Thank you very much for being here. I really appreciate your being here. For those of you who have been here for a little while, if you are finding value in the stream, I would wholeheartedly appreciate you slapping a like on this video. And if you're feeling particularly generous, you might consider sending a sticker or a super chat. Happy to have whatever support that I can. So, okay. So again, it doesn't look like there are any takers. There doesn't look like anybody's trying to, is very eager to submit their number that they got. So I'll go ahead and tell you what I got. I got x is equal to 1.38 times 10 to the minus 5. 1.38 times 10 to the minus 5. Shuk Ali says 1.38 times 10 to the minus 4. Are you sure about that? I think it's minus 5. Let me just check something real quick. Hang on. Yeah, you might have done a slight calculator error, but it's 1.38 times 10 to the minus 5. So we're going to move on and accept that as the value of x. So again, this is the value of x that we obtained by applying the x's small approximation. Okay, so some of you might have hopped into the stream a little late. Basically, we omitted this minus 2x from the equation to make our calculation much simpler, with the assumption that the value of x is much, much, much smaller than the number that it is subtracted from. Similar to if you were stepping on a bathroom scale with a marble in your pocket and then you took the marble out of your pocket, the reading on the scale would be the same. Doesn't mean the marble's weightless, it just means that it's negligible in weight compared to your weight, right? Okay, so remember, in order to check the validity of this approximation, what we need to do is we need to divide this by the value that it was subtracted from, right? So if we take that value, right, that 1.38 times 10 to the minus 5, I'll just go ahead and do it over here, 1.38 times 10 to the minus 5, and we divide that by the number it was subtracted from, 2.50 times 10 to the minus 4, whoops, times 10 to the minus 4, and I'll go ahead and just do times 100% so that it's expressed as a percentage. This value ends up being, what does it end up being? I have it written down. It ends up being 5.52%. Whoops, 5.52%. Now earlier, the PowerPoint slide I was talking about this, the approximation is only valid if the value of x is less than or equal to 5% of, or not less than or equal to, less than 5% of the number that it was subtracted from, right? So in this case, the value of x is greater than 5% of the value that it was subtracted from, and so this is not a valid approximation. So we cannot stop here, right? So at this point, we have a choice. We can either go all the way back to the beginning and use the quadratic formula to solve for x, or we can do something else. We can use the method of successive approximations. So to use the method of successive approximations, what I'm going to do is I'm going to take this value of x, this 1.38 times 10 to the minus 5, and I'm going to throw it back into the equation. I'm going to throw it back into the equation to solve for x again and see how that works. So I kind of wish I didn't erase the equation before, but let me see if I can. Okay, I'm trying to think of the easiest way to do this. Let's see. No, I don't want that. All right. Got a message in the chat, says, loving the stream, Ben. Can you shout out my chemistry teacher, Mr. Oh, man, I'm so sorry. I can't pronounce these names. Cloutier? He always sends us your channel when we're struggling. Much love. Oh, yeah, definitely I'll shout you out, man. I'll do one better. I'll give you a sulfur hexafluoride shout out. Hang on.
Hey, what's up? Got a shout out from Maxine Roy right here on this channel to Mr. Cloutier. Or Cloutier. I'm so sorry. I wish I could pronounce your name, but thank you so much for recommending my content to your students. I'd love to hear from you anytime if you want to do like a video call, like a live class with your students. I think that'd be cool. You know how to find me. You can email me, whatever. Get at me through YouTube. Anyway, I hope you've enjoyed your sulfur hexafluoride shout out, and I wish I would have known the correct pronunciation of your name from the beginning. So, all right, I'm going to try to get this stuff out of my lungs. Oh, yeah, stuff is just fun to play with. You know what I mean? I don't know. I'm surprised I still have some of that gas left. I haven't refilled my tank in a long time. I only save it for special important occasions. Okay, so I got a little bit off topic there. I apologize for that. So basically, what's happening is we solved for x. We made an approximation. It turns out not to have been a valid approximation because the value of x that we calculated is greater than 5% of the number that x was subtracted from. Okay, so what we're going to do is we're going to use the method of successive approximations to approximate it again, right? We're going to plug the value of x back into the equation where it was, and we're going to just keep doing that until the value of x is not changing very much from one iteration to the next. So again, I'm trying to figure out a good way to do this. I obviously need to erase some things, but I don't want to erase stuff that's really, really important. But unfortunately, like, all of this stuff is pretty important. So, okay. Okay. So now normally you would already have this equation. Maxine says, that was awesome. You got the pronunciation perfectly. Cheers, mate. Oh, that's a relief. I really hate mispronouncing people's names. All right. So, okay. So we're going to, let's see. I'm going to try, how do I do this? I think what I'm going to do is just kind of start over. Not start over, but I'm limited on the amount of whiteboard space that I have. So I'm going to write the equation, the equilibrium equation again in terms of x, and then we'll plug this value into it. So okay, so we had 1.67 times 10 to the minus 4. That's the k, the equilibrium constant given by the problem, right? Is equal to what did we say? 2x squared times x divided by 2.50 times 10 to the minus 4 minus 2x squared, right? So obviously the top, as we saw before, the numerator of this, it simplifies down to 4x cubed. So I'll go ahead and make that over there, 4x cubed. And so basically what we're going to do here is we're going to take this value, this 1.38,
this 1.38 times 10 to the minus 5 that we just calculated, and we're going to throw it right there. We're going to substitute it right there. And that's how we're going to solve for x. And we'll see if the value from this value, how that compares to the last value that we got. It will be changed a little bit because, again, we established that it was not a valid approximation. So it's going to change from one approximation to the next. So there's a lot of numerical work that needs to be done at this point. So I'll try to walk through it without skipping too many steps. But if anybody has any feedback, or if I say something that doesn't make sense, please let me know. Okay, so basically, so it's going to be 2 times 1.38 times 10 to the minus 5, right? And so that ends up being, what does that end up being? So that ends up being, I'll go ahead and see if I can just, all right, so I'll take that and I'll just drag this over here, right on top of me. Okay, so now I have a bunch of room. Great. Okay, so this is going to be 4x cubed divided by a very, very long expression. So it's going to be 2.50 times 10 to the minus 4 minus, and again, it's 2 times this 1.38 times 10 to the minus 5, which I have already pre-calculated to be 2.76 times 10 to the minus 5, 2.76 times 10 to the minus 5. And again, that's just twice the value of this 1.38 times 10 to the minus 5. And that whole thing is going to be squared. So if we take this value, 2.50 times 10 to the minus 4, and subtract away 2.76 times 10 to the minus 5, what does that end up being? I thought I calculated that one. Maybe I didn't. Yeah, I think it's 2 excuse me. That ends up being, I have a lot of numbers on this page here. That ends up being 2.22 times 10 to the minus 4, that squared. And so really is equal to 1.67 times 10 to the minus 4. And so basically, if you rearrange this equation algebraically, I'm assuming that you guys are all really, really smart. That's why you're watching my channel. You wouldn't be watching my channel if you weren't already smart, right? So once you sort of solve for x, basically what you're going to end up with is that x is equal to the cubed root of something really big, right? The cubed root of 1.67 times 10 to the minus 4 times 2.22 times 10 to the minus 4, that whole thing squared, divided by 4. So I hope you're following me. Again, all I've done is just algebraically sort of rearrange this equation here. So that would be the expression for the second approximation for x, let's say. Now, it's at this point that I would definitely like to recommend that anytime you're going to be doing problems like these, that you are very familiar with the calculator that you're going to end up using on test day. My personal recommendation, if it's allowed, is this calculator here. It's kind of a fossil because I used this when I was studying over a decade ago. But man, I mean, they are built to last. This thing still works. It's called the TI-30X2S. I'll go ahead and show you it's probably a mirror image, but yeah. Texas Instruments TI-30X2X X2S. I need some water. Hang on. What I like about this calculator is that it makes, like, scientific notation is very, very easy in this calculator. and you can type out a very, very long expression. I don't like to like calculate one number and then write it down and then insert that number somewhere else. I like to like solve for what I want and then literally just type the whole thing out all in one expression on a calculator to get my numerical answer. And this calculator does a very, very good job of that. It's not a graphing calculator, but if you need like a good scientific calculator, but you don't necessarily need, you don't want to spend a lot of money on a graphing calculator, I totally recommend this one. All right, so the next value of x, right? So solving this, I got a value of x equals, what did I get? I got 1.27. I'll do it in, I'll just do it. 1.27 times 10 to the minus 5, right? So the first value of x that we calculated was 1.38 times 10 to the minus 5. The second value of x that we calculated was 1.27 times 10 to the negative 5, so it has changed from one to the other. And so at this point, and again, we can do this as many times as we want. You know, we can do this over and over and over again until the value of x starts to become unchanged from one iteration to the next, right? So I'm a little lazy and it's getting kind of late for me. So I'm not gonna go through the trouble of substituting this value of x back into this equation up here and doing all this work again. Instead, I'm just going to jump to the next value of x that we would get if we were to do that, right? So if we were to take this value of x and we were to insert it back into this cubic equation here, the value that we would get would be 1.28 times 10 to the minus 5. And notice that 1.28 times 10 to the minus 5 is nearly identical to 1.27 times 10 to the minus 5. So by doing the second substitution after the first failed approximation, let's say, we end up getting a value of x that is acceptable, right? And so, again, with these equilibrium problems, it's easy to forget about what the question is asking. In this case, we are asked to find the equilibrium concentrations of H2 and S2. So we have our value of x. It's 1.28 times 10 to the minus 5. So I'm just going to lasso all this and delete it. No, not that. Oh, okay, good. So 1.28 times 10 to the minus 5, that's x. So for H2, right, I'll do it in blue. For H2, and again, we refer to our ICE table to look at the equilibrium concentrations, right? H2 at equilibrium is 2x, so that's going to be 2 times 1.28 times 10 to the minus 5, and that ends up being 2.56 times 10 to the minus 5 molar. So that's H2. And then for S2, at equilibrium, the concentration of S2 was simply equal to x, which is 1.28 times 10 to the minus 5 molar. So that is how to use the method of successive approximations. It's still a lot of work, right? I mean, quadratic formula is a lot of work, but the method of successive approximations is also quite a bit of work. Equilibrium problems in general tend to get pretty long-winded, so that's why it's important to practice them, and you can become quicker at them, and also more confident doing them more quickly. So that'll save you time, precious time, if you're in the event that you're taking a test on this kind of thing. All right, guys, so that does it for the equilibrium or the educational part of the live stream. I really, really appreciate your being here, your participation. And next week on May the, let's see, today's the 9th, so next week is going to be the 16th, right? So next live stream will be the 16th. I think it's going to be one more equilibrium live stream, which means we're going to have to move on to another topic soon, which means I am all ears. You guys can recommend any topic, and if I get enough suggestions and recommendations, then I'll start covering that material. So I like to listen to feedback. So, all right, thanks again, everybody, and all right, take it easy.